Hello and a warm welcome to this tutorial and overview of curved folding. I'm Joshua and today I'm going to introduce you to curved folding and the whole process from digital design to manufacturing at the digital design unit. Curved folding is a very exciting field of research and design application which I would like to bring closer to you. The computation and the design of curved folding geometries is still very challenging nowadays and is therefore an interesting research field for researchers worldwide. In this video I will explain to you the advantages and exciting features of folding in design and architecture and show you a simple and currently efficient solution for digital design in Rhino Grasshopper with the add-on Kangaroo by Daniel Piker. After that I show another method, create truss-like structures. You have probably already seen that if you fold a surface or piece of paper several times, you can increase the stiffness. In this way, surfaces can be designed as supporting structures and the design intention can be integrated into the construction. The first known curved-creased folding study is from a student work from the Bauhaus course by Joseph Albers from 1927 to 1928. Since then, some researchers and artists have been working in this area. To understand how curved folding works, I will briefly show the basics of it. The easiest way is to show it on a sheet of paper where you draw an arc in the middle. If you fold the sheet along the curve, you get a curved fold. Now place the paper on the table in such a way that only the folded edge touches the table completely. The table can be described as a reflection plane. If you measure the angle of incidence and reflection on both sides, you will notice that they are identical. A very important observation can be made by increasing the degree of the arc or decreasing the radius of the arc. There is therefore a relationship between the degree of the folding curve and the angle of the folding. This is one of the most important aspects to consider here. With this knowledge you can now create complex shapes. So we start directly in the Grasshopper file for task 1, which we prepared for you, and it should look like this. And we can close or minimize Grasshopper and go to the perspective mode and change the display mode to, for example, Arctic. And when we double click on perspective and double click on top view, can also change it down here. And also at the top view we can change it to Arctic. It depends how you like it, and yeah, I will stay with this one. And then we can open Grasshopper again and we will go through this file together. First we start creating a node, which is this one right here. And then we run a folding simulation, which is this part right here. And then we receive visual feedback and information if here is everything alright. And yeah, let's start with the node construction. Here we have some sliders which you can use to modify your node. Before explaining how we create it, I will show you what you can do. Here you can, for example, change the origin. Can change the overall size. And then we have here 6 sliders for 3 points. And these points are located here. So one here, and one here. And we can
change the position of these points and also the distances to the center. Then we can change the curve degree and also the offset distance of the inner surfaces. And here also the offset distance of the outer surfaces. And also the resolution, so the number of segments. And here these two Boolean toggles, I would leave them as they are right here. And on the right are the outputs. So for example, here the boundary, and here the folding edges. So we constructed this tool for you to create a node like this. You can also create this node directly in Rhino. And if you are interested how this tool works, we will go through it quickly. So it's located right here. And here we have all our input numbers and booleans, so from the number sliders. And so we start with an origin point and then a curve and also points on the curve. And then we receive the vectors from the origin to each point and can draw lines. So we have our first node. These are the baselines, and with these baselines we can create start or more points like this one, which I call bevel points. And then we need some vectors, and then we create lines with these vectors for the offset and create more points. And we create polylines with this offset and round everything, so with a fillet component or with just NURBS curves. So we receive our rounded curves, and these are our folding edges. And then at the end we have to offset them with the offset component. So it looks quite complicated right here because I put some more options right here, but it's as simple as that we need our folding edges. We start with the baselines, so 3 baselines in this example. Then we have here our folding edges, and when we offset them with the offset component, we have our boundary. Then we can loft them. Also interesting is that we have here a curve, or we have here curves, and we reconstruct this curve to a polyline. And we do this by dividing this curve into segments or points, and the number of segments can be set at the beginning, which I called resolution. And yeah, therefore you receive here a polyline, and we offset this polyline. And then when we loft it, we receive these ruling lines, and these are very important for the node construction. And yeah, that's all you need to know about the node construction. And yeah, for simplicity, we have made it available for you. So now I will explain to you how the tool for the folding simulation works and how you can use it. And After this, I will explain to you how it works and how to use the Kangaroo add-on. So we start here. I recommend to set the degrees to 0, and here we can reset the simulation. Currently it's set to false. When we set to true, the folding simulation will start. Here we have some display options. You can display this node in the middle as a B-rep or as or a planarity test. And you can hide it or display it as a mesh. Here we can set the boolean to true if we want to unroll it. If you have difficulties with the computation time, you can deactivate the unrolling, and I will set it to true because we get visual feedback if everything works. And yeah, now I will start the simulation. I will switch from the top view to the perspective view. Okay, I reset everything, and then I double click on the boolean toggle. And now I will increase the degree value right here, and I start slowly. Oh, and here we see that we can't see the folding, so I minimize Grasshopper and go here under display to edit Arctic setting. Then a window will open, and here you have some options on the ground plane. And at the moment the ground plane is set to 0. We have to set automatic altitude and press OK. Then we can open Grasshopper again, and I will reset the folding simulation, set to true, and then we can start again. I start slowly. Put the slider at the desired position. Here we can see the angular deviation, and it needs to be as close as possible to 360 degree. And here you can see that the numbers are switching, but if you take a look at the unfolding right here, and you don't see here some cracks or lines inside this geometry, and here it's displayed true, then you can stop the folding simulation and set this boolean toggle to false. Then you have your geometry. And here on the right you have your folded geometry and also your unrolled geometry. So to understand what planarity deviation and angular deviation stands for, these are two targets which we want to maintain. So the first target is that we want all surfaces to be planar, so they can be unfolded. In this case of curved folding, this is necessary. And on the other hand, we want the angular deviation to be as close as possible to 360 degrees. And this is because if you take a look at one vertex, for example this one right here, and then measure the angles from all the other vertex around these vertex, they will sum up to 360 degree at a flat paper. And if you fold the geometry, you also want to be 360 degree. Otherwise, the geometry would be broken. And for the folding simulation, it's very difficult to achieve this two targets. So yeah, these are the two targets, and here you can see how we receive the information if the surfaces are planar or what the angular deviation is, and so on. So you can take a closer look how we receive this information. And now we will go through the Grasshopper definition. So Kangaroo works with a solver right here, and Kangaroo wants some goal objects, and here we define them. So I start at the end of this definition. So we need some goal objects, for example, anchor points, so points on the 3D geometry which can't be moved. And then, for example, a length component. We can define that the length of the edges can change when it's deforming. Then we can define with the hinge component which edges should be foldable. And yeah, so these are the goals, and we connect them with an end wire component, and then with an explode component we can receive our informations. And this is the basic structure of the Kangaroo workflow. And here now I will go through how we can receive our geometries for these goal objects. So I will start at the beginning. So here we have our input geometries, so our B-reps. Then we create meshes and clean them up, and then we triangulate them, and with mesh edges we receive all the edges. We can use them for the length component. So this is the first part, and then we need their anchor points, and therefore we use face boundaries. And in this case we want only these 3 points or vertices to stay at the same position, and this planar face in the middle stays at the start position. So here we just filter the amount of lines per face. So here we have our mesh, and here we have our face boundaries. So for example, this face right here has 4 lines or 4 edges, and this face right here has 3 edges. And then we can measure the amount of lines with a list component, use a sort component, and then we receive the list or the face with only 3 lines. So this works only with a node with 3 baselines. If you want more baselines, for example, you need to adjust this right here. Yeah, therefore we receive our anchor points, and we can use them for the anchor point component. And finally we need the hinges. So here we can use the Kangaroo component hinge points, and then we use these 4 outputs, and then we connect them to these 4 inputs of the hinge component, and we do this 2 times, and afterwards we cull them. So we need to create a pattern, and here we right click on this cull pattern component and invert it, so that we receive here all the other hinges, and here we receive the hinges we want to fold. When we connect the first and second output to a line component, then we can see here that these are all hinges, and we only want the hinges at the folding edge. So these ones right here, and we can receive them if we have a mesh. Can use the warp weft component, and then we have these lines and also these lines, or we can manually bring them right here without this automatic solution. And yeah, here we have our folding edges, and then we will filter all the hinges. So every midpoint represents a curve segment, and then we measure the distances from these midpoints to these midpoints. And if the distance is 0, we know which hinge is the right one. We sort them, and then we have a list full of Boolean values. And then we can use a cold pattern. And here we use the cold pattern components, but we can't see anything because it's a Kangaroo component. But we can visualize this when we use these two cold pattern components right here and use our hinges and insert them right here. And then we can see we culled every unnecessary hinge. And here we invert this pattern. And so here are all remaining hinges. If we insert the lines, we can visualize it if this works. And then we can just use the components right here and insert them to an envir component. So this is the basic structure. We have to find our geometries, and then we can use our goal components and use a Kangaroo solver, and then we receive our mesh. For the second part of this tutorial, we open the second Grasshopper script. Here on top you receive informations on possible Grasshopper add-ons, and on the right are some inspirations for this Grasshopper script, and you can find here some research papers by Shajai Bhushan and among others. For the second part, so for this Grasshopper definition, I have to mention that we don't use the Kangaroo add-on, so we don't use physics simulations or optimization software. Here we use only geometric operations, and these geometric operations are not 100% accurate when we unfold it again. But we have worked out a workaround which works quite well. And yeah, we will go through this together so you can create your own geometries. And here we only work with geometric operations to be able to create larger geometries and more complex curved folding. So we start with the input geometries. Here we have prepared 3 options for you, and we have to insert a B-wrap, a closed B-wrap right here. So it should be a closed B-wrap with only planar faces, so for example a polyhedron or a Voronoi cell, and we can start with the polyhedron. If you want to use this, you have to install an add-on. You can open the package manager and search for Rhino Polyhedra right here, and then you can install it. Here you also see the version which is used for the creation of this component, and you can install the same version, which is this one, to be on the safe side if you want. And then we can visualize this. Here we have our B-wrap, our closed B-wrap, And we can right click on this component and enable the preview. So here we can scale the geometry. And if it's too small, we can also double click on the slider component to adjust it right here. Or I will just create a new slider component. Then we can change the scale. And we have here two options. And here you can see I enabled nodes with more than 3 connections. So you can see here is a node with 4 edges. And with the first slider, we can select some objects. And we can change it to nodes with only 3 connections. So you can see that we have here a node with only 3 edges. And for this option, we have to use the second slider, the B-Rep or geometry component to the input component right here. And then you can see the first results. And with this script, you are able to create a whole polyhedron. But in our case, we want to cut the geometry at the XY plane. Here at the beginning, we can change the height where we want to cut it. If we don't want to cut it, we have to move it up. And you have to adjust something right here. Yeah, it's just a small component, so you just have to disable this component if you don't want to cut through a XY plane. So you set it to false. But now we want to cut it through the XY plane, so I leave it at true. And here you can change the offset distance, so the inner surfaces. You can change the fillet radius. And you can change the resolution, and the resolution is important for the folding simulation. And if you have problems with the folding simulation, you can decrease this resolution value. So we can enable the Arctic mode and go to Edit Arctic Settings. And then we have to disable automatic altitude. So it's set to 0 and click OK. And then we only see the upper part of this geometry. And then we can start the folding simulation to set the Boolean toggle to true. And this can take some time. Okay, here we receive our visual feedback. So I switched the geometry. So if you don't like your input geometry, you can just disable the folding simulation and change the input geometry and then run the simulation again. And with the folding simulation, you receive the visual information about the folding depth, and you can increase it if you want, for example 9. And then you will see that it will change right here. And I recommend, if you want to change something right here, so the upper sliders, I recommend to disable the folding simulation. And yeah, I will disable it again for now to show you the other two options. Therefore, I press the Control key and right click on the output and connect it to the input, so it will be disconnected. Then we can take a look into this component right here. And you can also take a look inside these clusters if you want. And here we create truncated pyramids. And yeah, you can also use them I don't think that I have to explain here something, so I will go on with the next component. Here we create Voronoi cells, so you can visualize the information. You have a box with points in it, and these points define the shape of the Voronoi cell. And yeah, you can change these values right here and then use the brep component as the input. We can test it. And here we can see that we have to adjust some things. And when we use the Voronoi cell as the input geometry, it is normal that we have here some intersections, but we have to move the geometry down. So we cut the geometry somewhere right here. And we can also see some intersections right here. So we have to decrease the folding depth or increase the offset distance of the first surfaces, of the inner surfaces. So with this component. And yeah, for this I will disable the folding simulation so we can work better with these settings. Then I will change the cutting height. And here it's also very important that you don't cut through. Here you can see the nodes, so the triangles. This could be other shapes too, but in this case, these are triangles. And we are not allowed to cut through these triangles. So it won't work. So we have to keep that in mind. So these triangles have to be under the XY plane completely. Also this edge right here. So now everything is covered. All triangles are under the XY plane. So we can continue with this. And I will decrease the folding depth to, for example, 6. And then we can start the folding method again. So here we have no intersection, that's nice. And here at the bottom, the intersection is normal, so you can ignore it. And it's below the XY plane, so it's not part of our geometry. And yeah, that works nice. And I will disable the simulation again to show you two things that you also have to prevent. And therefore I will change the input geometry. For example, this one here, you can see that we have some openings and this opening is too small. So this geometry won't work. So we have to keep in mind that the openings are large enough so that the generated folding surfaces have enough space. And here we have also a small opening and a sharp angle which we have to prevent. So if we have sharp angles right here, the folding will be crumbled and not be as smooth as we want to. So we have to prevent these two things. So for the next steps, I will continue with a polyhedron. We can disable the folding simulation and go on. And now we can enable the cutting plane preparations. Here we have some values in this list. I will delete everything And we have here some numbers on this geometry, and we can increase the size. So like this. And here we have to set the Boolean toggle to true because we cut the geometry at the XY plane. Here we also set this Boolean toggle to true because we want to display the indices and numbers. And now we can select the numbers, so the positions where we want to cut the geometry, because in this state it's not possible to unroll this because we have here a loop. So every time when we have a loop or a closed circle, we need to cut it at one place. So now you can decide, for example, index 1 and index 3. But to do it efficiently, I will just use two numbers. So maybe 1 and 7. And in this case, this should work. And then we cut through these loops. Then we can change the geometry of the cutting objects. They have to cut through this whole geometry. If it's too small, we have to increase it. And it's important to keep that in mind, because if later there's something displayed incorrectly, then you should take a look right here if the cutting object is covering the whole stripe. And the depth can be set to 0.1. Sometimes it could be necessary to set it to 0.2, for example, if you have problems, and you can try this as a solution. And here you can change the resolution again for the laser cutting. And this should work. So we can start with the unrolling. We double click on this component and we can change the position. And here we can see that it worked. We have just one part which forms an S. And I can show you if we, for example, cut it through 0. I will insert here the number 0. Then we receive two parts, and you can change the layout, so the spacing. And it's up to you if you want to save space on the laser cutter, or if you want to save connection parts, then you can just create one part, then you have less connection parts. Then we can go on, and here we have the folding depth, which we set at the beginning right here. And sometimes it will work for the first folding simulation, but for the unrolling it could be problematic. So you can change it right here, but I recommend to change the folding depth here. So keep in mind to take a look if this could be a problem if something is not working well. And yeah, then we have some options for connections and text. And we can use chords or strings for our geometry. So we can create here a lacing pattern. And change the position and also the opening size. And afterwards, when we bake the geometry, we can also delete unnecessary openings and just receive a few ones if we don't like the appearance. And yeah, then also the text, we can change the position and so on. And these numbers give us information about which parts should be assembled together. And here on the right, we receive a list with informations. So here we can take a look. Okay, 2 has to be assembled with 5. So this part has to be assembled with this part. And this list will give us the information about this. And don't be confused. Every list will appear 2 times. So we have here 2.5 and here 5.2, which is obviously the same list. And yeah, but it's helpful for construction. And then we can create connections for screws, bolts, or eyelets. And we can also add more connections. And if we have to adjust the opening size, so for example, if you want to use screws or bolts like M3, we need a radius of 1.5. And here we can see that our geometry, our scaling is not suitable for this opening. So we have to scale our geometry. We can scale it right here. I will just type in 100. And then we have to adjust our offset distance. So here we can see that the unrolling is broken because the cutting objects are not large enough. So we have to increase the size right here. And then it works again. And we also have to adjust the folding depth. Okay, here we can see the size of our laser cutting. So this geometry is still a little bit small. So I will scale it up a little bit. And then again, increase the folding depth. And I will adjust the layout. And now our curved folding is very small, so I will increase our fillet radius. And this will also prevent the geometry from crumbling, and the curved folding will be more smoothly. And here the unrolling is broken again, so we can take a look. The cutting geometries have the right size. They are not small. But if we take a closer look, we can see that here a small part of a triangle is visible. And it should be below the XY plane. We are not allowed to cut through these triangles. So we adjust the cutting height. That looks fine. We can also run the folding simulation to check the folding depth, and this looks nice. We have no intersection, and then we can disable it again and can continue with our preparations. So here the cutting objects are still working. Here's everything fine. We unroll our geometry. And if you have to adjust something at the beginning, you can disable these components right here. So these preparations right here, because they are maybe computationally demanding. And yeah, now it worked. And we can continue with the connections. And we have to increase the overlapping. Increase the text size. And now we can take a look right here. Here we have our output geometries and also here the layout. And for the laser cutter, we have to change this here to 1000 by 600 millimeters. This is the size of the laser cutter at TU Darmstadt. And here we have our folding edges, our boundaries, our outer edges, and here are our openings with 3 millimeter diameter, so 1.5 millimeter radius, and also our lacening openings and our texts as curves. So before exporting our geometries for the laser cutting, you have to decide what type of curves you want to use for the folding edges. And you can use vector engraving, or you can also use a perforation with a specific pattern. Then you can use these curves and change them with a dash pattern component, and you will receive more information on Moodle. And if you do a perforation, you have to export it to a different layer for laser cutting. So for the preparations for laser cutting, we need our layer structure in Rhino again from task 2, the laser job RAM with the color white, vector engraving with red, or vector cut for inner or outer curves, cyan or green. And also make sure to set the line width for every layer to hairline. If you want to use, and we can start baking these geometries. So if you want to use for the folding edges continuous line segments, so these ones, you have to bake them to vector engraving bright, so vector gravur hell with the color red. If you want to use perforations, you have to use vector cut Innenkanten, also Vektorschnitt Innenkanten with these color values, or you can use vector cut Außenkonturen with these color values, so green. I will continue with the normal curves and bake them to vector engraving bright, so to the red one. Then we have our outer boundary. This belongs to vector cut outer contours, so Außenkonturen green, right click, bake, Vektorschnitt Außenkonturen. I will go to the top view. Then we have our openings. I will bake them to vector cut inner curves, so Innenkanten. Then we have our text, and I will bake the text also to vector engraving bright, so vector gravur hell, the red layer. And then we have the lacing. For now I will create a new temp layer and bake all these openings to the temp layer. And then I minimize Grasshopper or close it. And don't forget to save your Grasshopper file. Then I lock every layer except the temp layer. And then I can remove unnecessary openings. So the goal is here to leave an opening at a connection part or 3 openings at a node right here. So for example, here one, here one and here one. So that we can connect these three openings with a wire if we want to. So now we have deleted all unnecessary openings. We can unlock every layer again. Then we can right click on this temp layer and select objects. And then select this layer, right click and change object layer to vector cut inner curves. And then we can delete the temp layer. And yeah, just to mention it again, these additional openings are not necessary for polyhedra or polyhedron. But if you want to use a Voronoi cell or something like that, we recommend to use them to have more control over the folding. Then we can open Grasshopper again and also bake this rectangle here to laser job RAM. Then we can close Grasshopper. Then we can arrange our parts in this rectangle. Here you can see that here is still enough space, so we can create larger structures. Then you can save Grasshopper again, close Grasshopper, and then you can select everything. Go to File, Export Selected, and export your Rhino file for the laser workshop. I hope you enjoyed the insights into curved folding. Maybe it inspired you a bit and didn't scare you away from the complex Grasshopper files. And if you face any problems or have any question, feel free to ask us and we will try our best to support you during this seminar. Have fun creating your curved forms and see you next time.